Hello students, today's practical class we are going to see how to determine the wavelength of this monochromatic sodium vapor lamp using biprism and the spectrometer. Alright, so the aim of today's experiment is to determine the wavelength of the monochromatic source, that is sodium vapor lamp, using the Fresnel's biprism and spectrometer. You can see this is the Fresnel biprism, that is prism 1 and 2 is combined to form a single prism, and let's see what is the components required. So apart from Fresnel biprism, we require the spectrometer, right, and then a sodium vapor lamp, and then the scale and telescope arrangement, which is we are seeing now. To begin the experiment, the biprism is installed in the grating stand, as you are seeing. Okay, this is the biprism which is installed in the grating stand, and usual initial adjustments of spectrometer are adjusted, and now the spectrometer is ready for observing the fringes formed by this biprism. So after adjusting the initial adjustments, the slit screw is adjusted for slim image of the slit inside, and the collimator screw is also used to adjust the clarity, and the telescope screw is also adjusted to see the clear image of the images formed. So you will actually see two slit images inside the telescope view. The telescopic view shows the two images of the slit. Now the value of x0 can be measured from these slit images. That is, x0 is nothing but the distance between the two virtual images. To calculate the value of x0, we are actually going to record the readings for x1, that is the coincidence of the slit image 1. We are going to use the mirror and this scale arrangement to take the reading x1. So initially this telescope crosswire is adjusted to match with the first image of the slit, which is seen in the telescopic view, and then the scale and telescope is adjusted so that the image of this scale, which is reflected from the mirror strip, can be seen in this telescope, and the crosswire of this telescope is adjusted to coincide with the scale reading with respect to that slit image. That will be taken as. Now the telescope is adjusted so that the crosswire of this telescopic view is matching with the second slit's image, and once again the same procedure is repeated. That is, the scale reading in this telescope is made to coincide with the crosswire, and that reading is taken as x. So from the readings of x1 and x2, we could calculate the value of x0. Generally, to measure the fringe width, the fine screw adjustment is used to coincide the crosswire of this telescope with the concerned fringe, and then the scale reading, which is reflected from the mirror strip, is taken in this telescope. So that will become the reading for that particular fringe, which is matched in the telescopic screw with that crosswire. So in this experiment, actually we are going to measure the fringe width by forming the fringes through parallel rays method and divergent rays method. In both the methods, we require B value and D value. Similarly, in divergent rays method, we require A value also. So let's see what is A, what is B, and what is D. So in the experiment, the distance between the slit and the biprism, this is going to be A, and from biprism to the crosswire of the eyepiece, That's going to be B, and the distance between this mirror strip and the scale and telescope, the scale, so that is going to be the distance, capital D. To form the fringes in the parallel rays method, we are going to remove the lens, objective lens of the telescope, and then we are going to see the now I have removed the objective lens of the telescope, and now you will be able to see the fringes formed in the telescopic view, and from the fringes we could calculate the fringe width. To calculate the fringe width, actually we are going to record the scale reading, which is actually reflected from the mirror strip, that you can see in this telescope. You can see the telescope and the scale arrangement. The scale reading is actually reflected from the mirror strip, and that can be seen in the telescope. So that scale reading can be adjusted to the cross wire for the fringes. Any fringe can be taken as N, and the scale reading can be noted. Now subsequently the telescope screw can be adjusted to view the second scale reading for the next set of fringes. Like the fringes can be recorded for n plus 3 or n plus 4 likewise. So the observed scale reading can be recorded in the tabulation shown. For example, the fringes can be taken as n plus 10, n plus 20. If even more fringes are available in the view, of course we can have the readings for n plus 10. For example, if few fringes are available, then the reading can be taken as n plus 6, n plus 12. Likewise, the scale reading can be recorded. From the scale reading, the shift for that particular number of fringes can be calculated. Then the fringe width of the single fringe can be recorded as shown. This is for the parallel rays method. Now the second part of this experiment is to observe the fringes for the divergent rays method, for which we are going to remove the objective lens of the collimator also. Now you can see the fringes in the view, and compared to the parallel rays, that method, number of fringes can be reduced here, means the fringe width likely to increase in this view for the divergent rays method. That fringes can be seen, and then once again the scale reading can be recorded through this telescope, and any fringe can be again taken as n, and then the scale reading in the crosswire can be recorded, and subsequently for different number of fringes like n plus 4 or n plus 5, depends on how many fringes are available, the sequence can be set and the observation can be recorded in the notebook. For divergent rays method, the fringes are set as n plus 6, n plus 12, or if less number of fringes are available, you can make it like n plus 4 or n plus 3. Their scale recording can be subsequently recorded, observed and recorded here, and the shift for that particular number of fringes can be calculated, and for single fringe width you can take the mean value of these all readings and you can use it for the calculations. So using the beta, that is the fringe width calculated from parallel rays method, and beta dash from divergent rays method, the wavelength of the monochromatic light source can be calculated using these formulas. For example, this is for parallel rays method. you can have the formula lambda is beta into x0 divided by 4d square into b. If you substitute all these values, you could calculate the lambda as 5860.8 into 10 to the power minus 10 meters. Similarly, for divergent rays, of course, this formula can be used, that is beta dash into x0 divided by 4d square into ab divided by a plus b, and you can substitute these values and you could calculate the lambda value as, of course it is shown here, 5266.7 in 10 to the power minus 10 meters. So by taking the mean value of the two wavelengths measured from parallel rays method and divergent rays method, we could arrive for the value of the wavelength of the monochromatic light, that is sodium vapor lamp, as shown in this result.